Okay, so good evening, everybody. Seems we have few less today. Don't know why, but maybe people are slowly getting into the end of the year. There's one more coming. Okay, so for today, it's I thought I go a bit more through RNA-seq, maybe go through the stuff we did last time, recap a bit what we did, because that was a lot, and see how far we get this time. I have to admit the things are not that well prepared as I would have hoped, because this week was a bit too busy with things, but let's see how things work. So, to remind everybody what we did, and has been lost just SDS. No. What we did was that we worked a bit on RNA-seq data, and we used this example file from, do I still have this here? Just a second. Computer crashes are annoying. So we used this example data from this airway smooth muscle cell data set. So to remind everybody, this was an experiment where they used lung tissue from 4 donors and derived smooth muscle cell lines from this, and when they tested the effect of 2 drugs onto it, dexamethasone, which is a glucocorticoid, and what was the albuterol, which is a beta-2 receptor agonist, and hence also is used to relax smooth muscles, which is the stuff which you usually have in asthma inhalers. And we wanted to see how the transcriptome changes. And I used this because it's always our standard example to explain RNA-seq. I used that one and showed you how to get through the whole data. Through this whole procedure of getting your reads, aligning them, and so on. So, maybe things work this time, and we have here a working network connection. So, it would be really useful if this now popped up. Otherwise, I have to do it all by memory. Yep. So I wanted to give you all a sort of recap of the commands we used last time and write it all down and put it on the web page. Somehow I didn't quite manage, so this is how far I got. Now we can go through that together. What we started with is with this gene expression omnibus thing, and we quickly go over to Sean because I did it. This is H minus X. We can probably just go through the process once more. /aux2/airway. So, here we go. We started off with downloading all these reads here, and here's the list of all the reads. And maybe before we look at the list of reads, we should look at our sample table. That's always the very first thing you should have in your RNA-seq experiment, is obviously a sample table, because you typically have lots of samples. You need to know what is what. And here is the sample table that I downloaded for this data. I show it to you once more. Each sample has something which we call a run ID, which is just the number under which the data was deposited in the FASTQ archive. They use these 4 different cell lines, which are just smooth, airway smooth muscle cell lines from 4 different donors. And for each cell line, they have 4 samples, namely the control, which is untreated, the treatment with the 2 drugs, and the treatment with both drugs. And we have hence a total of 16 such samples. The samples are sequenced paired end. So that means that from each fragment we sequence both the 5' and the 3' end. This is why we have a total of 32 FASTQ files. To remind you how these look like, I quickly look into them here. And you see in these FastQ files, each read is represented by 4 lines. The first line is always a read ID, which tells you something about where the read comes from and how it it's usually some kind of arbitrary idea. If you get your FastQ file directly from the core facility, it typically has something like this, which is the serial number of the Illumina instrument and the position where exactly the read was in the flow cell, but it's hardly ever of any use to know that. Then comes the actually interesting part, the sequence. Then comes the plus sign, and then comes this here, which is the quality string. We quickly talked about this last time, that this is some weird code where capital letters usually means that everything is fine. What people now like to do next is that we do a first quality control step, that we use tools like, for example, FastQC, the FastQ quality control tool, which I often get credited to be an author of, which I am not. It's not written by Simon Anders, but by Simon Andrews, who is nearly me. I once met him. He's at Birmingham in Cambridge. So he has written this tool, which is a nice tool which basically visualizes all these quality scores and shows you how many of your reads have good qualities and how many have bad qualities. Even though he's my namesake, I hardly ever use this tool, because if you do RNA-seq data, you don't care that much about read quality. Either we read align somewhere, like your alignment program finds a unique place where this read aligns, and tells you that it comes from there, when you don't care if you have some read errors and if a few bases are wrong, because all we want in these kinds of experiments is to quantitate expression. We want to know for each gene how strongly it was expressed. We don't care whether there's any mutations or somatic changes or whatsoever in the read sequence. If you're doing a resequencing experiment where your aim is to detect mutations or somatic mutations in case of cancer, this is of course a very different matter when you care about whether every single read here is right. But if we only want to know gene expression, usually these 50 base pairs are more than enough to find a unique position in the genome where it comes from, unless it's a repetitive sequence. But if it's a repetitive sequence, it's probably not transcribed anyway, and if it is transcribed, you probably don't care about it. And if you do care about it, for example, because you might work on the centromere, if some of us do, then of course you need all kinds of special stuff. But for our very simple standard thing, all we care about is roughly where it comes from, and in that case only if it's from some kind of processed and probably coding transcript or long non-coding RNA or whatsoever. What we did, as you see here, for each read we have 2 FastQ files coming from both ends. Then the next thing we did last time is that we made us a genome reference file, because if we now want to search for each of these things where it came from, we need to find out where it is in the genome. And for this we first need to know the genome. So we downloaded this file here, which, as you might remember, is for a full human chromosome, starting with 1 and starting with a few pages of ends for a telomere, and now we actually see the thing. Then the next thing we did is that we used this FastQ file. Now the next thing we need to do is to choose an alignment program. There's about, it feels like a million different alignment programs, which is because writing an aligner is such a classic computer science problem. Finding one string which matches to another string is sort of really in the algorithms of data structure lectures in a computer science curriculum. It's what learning ecolo is to a biology curriculum. So everybody who studied computer science thinks, I've learned how to do this in my lectures and I can try this. So of course you try that, especially if you don't have any other good idea what to write your PhD thesis on. But occasionally people do have good ideas, and that's crucial because the standard algorithms that you learn in your computer science curriculum they are not exactly optimized for the specific case of having literally 100 million short sequences, which we want to find in one single long sequence of 100 million base pairs length. And lots of ideas went into that, and there's all these different ideas. The Burroughs-Wheeler algorithm and the seed and match algorithm and whatsoever. And the outcome, what it means for you, is usually two things: speed and sensitivity and memory consumption. Speed is important because the aligners that we had in our first round of next generation sequencing, they would easily take hours to align the maybe 10 million base pairs which you got out of a first generation Illumina run. And if we still would use something that slow for the 1000 genome project, we would get nowhere. So luckily, a lot of progress went into that in the last 20 years, or 15 years. Since when do we have Illumina now? Quite a while by now. The issue how to choose it for you is hence A, is it fast enough for your choices? B, does it run on your computer? Which typically does not mean that you need an expensive computer, but all of these things usually run once you have 16 gigabytes, which is standard for most computers unless you buy a really cheap laptop. Or at least for my laptop here, I had the option of getting it with 8 or 16 gigabyte. I think one was 1,000 euros and the other 1,100 euros. If you ever want to buy a computer, spend the extra amount to get your 16 gigabyte RAM, but don't bother about all the other things of having a big processor or whatsoever. Next thing is, the next important thing is precision. Does this thing properly deal with slight mutations, short indels, like changes, 2 bases deleted, 3 go in? We don't care about this in RNA-seq. We do care about this in cancer resequencing. But we are here and not over there at DKZ. So all these things about how to find DNA mutation, this is basically the two big ideas. Either you want to find DNA mutations, or you care about RNA-seq when we need to do this thing. There's one specific thing you need for RNA-seq is these reads are long nowadays. We sequence typically 100 base pairs. The typical exon in the human genome has about 300 base pairs, so about every third read or so will jump over an intron, start in one exon and in the other exon. Most aligners come in two flavors. There's DNA aligners and RNA aligners. DNA aligners are optimized to work with resequencing projects, and they will not care about introns and will get completely confused. RNA aligners, I expect that there will be introns and that the reads will jump over these introns and will deal for this. So in the end, summing up this long story, if you choose an aligner for an RNA-seq project, make sure it's one meant to align RNA and not one which is meant to align DNA. It's surprising how people always manage to think lots of things about it, but then we get this one thing wrong. So I've decided to use ZapRead, which is an aligner which is labeled to be used for both. And most of these aligners, they typically work. Now we started this aligner here by first, as I said, taking our big FASTA file with all our genomic sequences, and you have to tell the aligner prepare this thing in a shape that you can quickly find something. This is called building an index. See if I still find the command. This was the command I used last time. I said ZapRead build index minus, and here I give it the FASTA file. I should maybe talk a bit more about using the command line here. If you want to work a bit more, learning how to use the command line pays off, because doing everything using the mouse is A, cumbersome, and B, it's not something that bioinformaticians typically do, and hence when they develop tools, they don't like to spend all the many extra days that you need in order to make a pretty but essentially useless GUI, such that those users who don't want to spend the 2 days to learn how to use a command line can also use it. So sorry about that. I always hear whenever I show stuff, people say, why isn't there a GUI? Why can't I use the mouse? It's not so hard to learn how to use a command line. There's plenty of tutorials on the web. The crucial point about the command line is what we are using here is called a POSIX command line, so a command line used for Unix. essentially the command line on all Linux machines and all Macs are more or less the same. You just open your terminal, or I think the Mac people also call it the terminal, and work always the same way. If you have a Windows machine, then your terminal will work completely different, and installing all the software will be a thing. So use Linux if you don't want to use a Mac, but don't try to use Windows for this kind of stuff. It's really not worth the effort. The reason why the Mac works is because it is actually Unix. These command lines, they always, there's a few things which are useful to know about the command lines. First, there's a couple of standard commands, for example, ls for list the content of a directory, so that you see all the files. There's cd to change the directory, you might have noticed me doing them. And then if you want to run a complex command like my build command, here it always starts with a command word, and this is an actual file. Somewhere on my computer, or in this case on the computer shown, is a file which is called subread built-in, and that file contains the code which I execute for us. And the computer needs to find it. Usually newcomers to the command line, the first problem they have, they enter the command and it says ABC not found. It will not look in your current directory for this command. It will look in its search path. The search path is here a list of files where it searches, and there's a certain standard way what you're using on. I don't want to spend too much time on this, but if you don't know what the search path is, look it up. Otherwise, you will never manage getting somewhere. So, the next thing is, for strange historical reasons, the file on which your command actually is supposed to work on typically comes last, and all the options come in the middle. So if I run this build index thing like this here, it tells you here how it should be used. Subread build index. You might notice a little subtlety, / in front. This is the exception to the rule I just said. It will look in the current directory if you write / in front. So somebody at the VHI in Melbourne got obviously tired by countless users asking them, how do it doesn't find my command even for it's right in front of me. So I write that / which won't work if you have installed it properly, but it will work if you have installed it improperly. So yes. The way how this is written here is you can see certain conventions. If you give a usage, there's always square brackets, means that something is optional, and things which are not in square brackets are things which must be placed. So we must always write something like -o base name, and we must put something like faster file 1. But it's optional to add a faster file 2, and it's optional to add options. Options always have the shape of a minus sign followed by an option character, and then maybe or maybe not some extra thing, and here you get a list of all the options. We haven't used any other options except for -o. Build. Yeah. And this is how it looks like. Our command, we have here the output file, which I called index/crch. So within the subdirectory index, it should have these things, and then the faster file. If I now look in my directory in which I have worked, you see I made a subdirectory called index here, and if I look in this subdirectory, I see all these files. For those who feel uncomfortable with this, of course, you can also do it like this and go simply. No, you can't, because I'm not on my working on my laptop, but working on a remote computer now. But I could go. So, and here we have all these files. I can give my ls also extra options. For example, -l -h, and then it gives me the long form and shows me how big these files are. Or I can put them together in one thing. So, next thing. Now we have our index. Our next thing was to align the files. And for this we used the command subread/align. And again, you see here it gives us an index, it gives us reads. This time we have -r for the first read set and -R for the second read set, and then an output file -o for the BAM file. And then this extra thing -to, which is a bit unusual, but if you go back, you remember if you type this just like this, you get all these explanations. Yeah. And of course, there's a 20-page FastQ manual which explains all these things in a bit more detail. What we also did last time is I was a bit worried that if I now want to align all these 16 files, I might start messing things up. Like I might mess things up, like mixing up which reads should give which BAM file. And so I wrote a little R script which writes all these things here in one thing. I showed this to you last time. Now we have the alignments when we used the feature count command, which, see if we can still find it, which is also part of the subread package. And it wasn't a feature count table. Yeah. And that one takes all these alignment BAM files and produces the count table, which we then worked with. And so this is your usual strategy. You first get your FastQ files, you build an index if you don't already have one, because once you have built if you always work with mouse, you have to build the mouse index only once. So get your reads, build index, align the reads. Then you use some feature count program to get the count table, and then you can work from there. So the one thing, let's now go here and open the count table. Do I still have it? That was the one thing I wanted to start last time. Yeah, exactly. Here I loaded the count table last time, and now I have here this huge table where you see here is all the on the top are all the count files and the different alignment files, and here are the gene names. And the numbers tell us how many reads have fallen into each gene. One thing I haven't done last time and I thought I should quickly show you is there is a tool called the Integrated Genome Viewer from the board, or IGV, which I have installed here on my computer. And what this thing allows you is to look a bit into this BAM file and look at the individual alignments. And it's quite helpful to see this one. So let's run this. File, load from file. Am I here in the right thing? So this. Zoom in to see coverage. Still no. I thought I've zoomed in enough by now. Chromosome. Okay, maybe I don't get it to work now because it seems to be unhappy with this small screen here. Now here you now see how these read alignments typically look like. Let's see if we find some place where we see a bit more. How can I now zoom out if it doesn't show me the zoom out thing? Damn it. So here you see two genes at the bottom which sit here, and here you see the individual reads. And as you can see, many of these reads here, they start here, align in one thing, and they align and they give this. And here are reads which jump over the intron. They start here, and then they jump over it and go on and on all the way to over there, which somehow unfortunately doesn't properly fit on my screen, that I could show them to you now. The important part that I want to see you here is, and which you can't see. What do you do if your screen is too small to see the button that you want to see? Now I can't zoom out. So what I want you to see is how uneven the coverage is in these things. RNA-seq reads don't sit at RNA-seq reads don't sit only at the Yeah, it's really a bad thing. What I would hope to see is that over the axons you always see the signal going up and down and up and down. So there's always stretches which have hardly any reads and other stretches where 6 or 7 reads pile up on top of each other. This is PCR bias. Some fragments amplify much better than other fragments, and so after your 15 rounds of PCR amplification, you see suddenly from some parts of the genome, you see much more reads than from other parts of the genome, simply because PCR efficiency are quite different. We don't use specific primers, we use random priming here, and we use random fragmentation. We don't have any standard curve as in qPCR, so things vary wildly, which of course means that you can't take RNA-seq output too literal, but all these biases, they will be the same from one sample to the next, at least if you take care that all your samples are prepared in parallel, like in the same PCR strip in one thermocycle round, and then you can compare them well. Otherwise, things get a bit more complicated for comparison. So now, and it's also useful to look at these BAM files and this alignment occasionally to see a bit of what's going on there. So now let's go on where we stopped last time, because we wanted to see a bit more what we can do now with our feature counts file. And what I did last time, should I use this one? I actually wanted to use the other one, which I had already downloaded. Sorry, quick. So you might remember last time we used only a truncated FASTQ file, which didn't contain all the reads. So I would like to use the total reads, and I don't want to download all FASTQ files. And if you work with public data, this is a great resource, because it allows you to see for basically all the data, which is several tens of thousands of studies which are deposited. You get just the read count table. So I will quickly show this. We are looking for the one with 16 samples, which somehow had DEXA. Come on. 0 to something like this. 5. Yes. I really need to replace this thing here. This was the one. So here is the one we used last time. I download the counts here. Here we have it. Extract. Where do I put it? Let's put it here to temp. Extracting completely counts gene. So I use my R session. Let's start with a fresh R session now. File, new file, R script, library tidyverse as always. And now I read my file. Read ESV, tab separated. And I think I just put it now to temp, and then, how did I call it? Counts gene. So now we have here our file, which you see contains here the all these read IDs, and at the bottom it has here as the last one the gene ID. First thing we can do, if we have something like, let's do our standard analysis as we did last time. So this thing here is something where it's actually a matrix. It's not so much a typical tibble table, it's a big matrix. So I want to convert it into a matrix. So for R, the difference between a table and a matrix, in a table each column can have a different data type. Some columns might contain integers, others contain real numbers, others contain strings, and so on. A matrix is one big rectangle of only numbers. So if I give this over and say as matrix, then we get this thing. However, you see here the very last row in this thing, gene ID. This contains this doesn't contain a count, it contains the ID of the gene. So I should first change this, and there's this command row column to row names, which takes such a column and changes it to something which is in front then. So here now you see this thing, and now the column has vanished, but if I now hand it over to S matrix, then we get this thing. So I take this thing and now let's call it count matrix. And now I have here lots of warnings and whatsoever. Count matrix. Like 1 to 10, 1 to 5, comma 1 to 5. This just shows you the first 5 rows and columns, and you can see how this looks like. And this is what we now want to work with. We have here these things are run IDs, and we need to know how these run IDs map to genes. So we load the run table. I hope I still have written down where is the run table, feature count run table here. Wait, delim run table. Yep. Okay, this has worked. So I load the run table. Again, read tsv run table. Now, where did this run table come from? I also downloaded it from your data. If it's your own data, you probably have made one of these yourself. And you see here my run table, they contain all these stuff which they considered helpful or useful, or what they submitted together with it. And I now will select, you remember the select command, which selects certain columns. So I select only the columns I need, namely run. How was the other one called? Cell line and treatment, I think. Let me quickly look here. Run cell line treatment, that's what I had. So here now we have them, and I had here the word run. I changed this to small letters such that it's consistent. Now we have here our run table, which works, which tells us what each of the columns in the count matrix are. One thing we need to make sure is that this fits together. I now got the run table from the sort reach archive. I got the count matrix from this recount database. Who knows whether the columns are in the right order? So if I look at the column names of count matrix, then you see there are here 9, 8, 11, 10, 14, 17, 18, 23. While here in my run table, they were properly sorted. So this is already a disaster. If I would go ahead with this, I would have all my sample annotation mixed up. I can go ahead with it. So the way how I would now go ahead is I load our DESeq2 package, and now I say new DESeq dataset. What DESeq wants is that you prepare one object which contains all the data, the count table and the annotation and so on. And I have a count matrix, so I use here from matrix. Now I give it first the count matrix, and then my run table. And then as last thing I explain this tilde1 I explain later. If I do this, then it says error number of columns in the count data and the number of rows in the column data. This is not the same. Even the number of columns doesn't fit. How is this possible? Dim count table, count matrix. This is my count matrix has 15 samples. Anybody notice where I left the 16th sample? I'm pretty sure it was 16 before. Let's see here. Here we have this thing here, a table with 16. Really? Okay. The recount project obviously has lost one sample in the process. What do we do now? Well, we go on with an unbalanced design. You'll see later how this works. We should reorder our run table, our count mat. We should remove from the run table the missing sample. So which sample is missing? I don't want to go out now and search it while you're waiting here. So we just go on without it. So here is Here are all our col names of these here, 9, 8, I can maybe sort them, and it's easier to spot which one is missing. 8, 9, 10, 11, 12 is missing. So the way how I might do this now, I take here my run label, my run thing, and I say filter, and I filter it now for those runs which are in the col names of count table, of count matrix. Now I have only 15. Let's hope that the sample wasn't important. Obviously, it's not something that should happen. Now, if I now do this, NA values are not allowed in the count matrix. In new way, I should have tried this before because that worked last time. Let me quickly check, is there any NA? Is NA count matrix? So now you can see a little bit how you debug sort of, because usually I always try everything beforehand. This time I didn't find time. So you see a bit the typical things that can go wrong. So of course I already have worked with this thing long enough. So I know a bit about what's happening. So I can use isNA to check if there's any NA values in it. It says false, but I don't want to look through all of them. So I say, is there any NAs in here? It says true. Now we can look, where is this NA? So I ask which tells us where the array is in the entry 190551. We don't quite know where this is, so the which command has an extra option called array index, which gives us the array. So in row 16440 there is an NA count matrix. See, hang. Let's look here. Row 16440, and here you see we have values for all elements except for this last, for this one. Who knows what's happened here? We can ask the people from the recount project how comes that there's data missing in it, in their stuff. For us, well, this gene here, what might this be? Sparta 2, never heard of it, probably will also work without it. So, okay, I take my count matrix and I remove this sample here, 16440. Minus 16440. You might remember, I think I've never mentioned it. Usually you give here, you know, in array indexes is always rows, comma, columns. And in R, if you give a number with a minus sign in front, it says everything except for that, is how it understands that. So now we run this, and now it has happily given us our data. What it hasn't spotted is that the column names of count matrix still don't match the row names of the run table. Col names of this one, you remember they have here 9, 8, 11, 10. Run table, $run, are 8, 9, 10, 11. How do I get my count matrix in the right order? I can take this thing and I can now take my count matrix. Let's say here head, so that you see the beginning of it. So these are the first couple of rows of this count matrix. And again, I can now give here which rows I want. All except for minus 16440. And now which columns, also all, but this time I specify the columns by their names. You remember run table $run. Seeing this up here is all the names. And because they are given here in a different order than in the count matrix, this will reorder it. If I now press enter, you will see this has now reordered the count matrix in the proper order. So this is something you can use with square brackets not only for subsetting, but you can also use it to rearrange columns and bring them in the correct order. So now I have this here, and now we should have everything that we need. So I make my object. We take all the count matrix, all the runs, and the columns in the order given by run table $run. Then we have our run table, and last we have a design matrix. The design matrix gives us, tells us what a kind of comparisons we want to make. And in this thing, and you will see later how this works, we now put here cell line plus treatment. So for now, the important thing, everything which turns up in this is the so-called formula. We haven't talked about formulae yet, but I hope we still find time to talk a bit more about ANOVA. And ANOVA uses this formula notation. A formula always starts with a tilde, and then it uses column names. In our case, we have only two column names, namely cell line and treatment. These are the column names in runtable, and we use them here. Now, if I do this, I get my DE-seq data set, and of course I have to save it in a variable. I always call these variables DDS for DE-seq data set, which is not very creative, but it's just how I've been doing it always. Now here is my DDS. And now we have everything together. We have this DDS where now the column samples, the treatment, and everything is in one big thing. And the thing that we did last time is that I now say DDS is DE-seq DDS, and let it run through this thing. It now does a couple of things. It estimates normalization constants, dispersion estimates, and other things. And then we'll get to basically up to where we got last time. It takes now too long what I did last time, and I will simply continue from here now, so that I do it easier, is that I subset subset to only those values which contain dexamethasone. Let me DE-seq runtable. Here last time when I did my runtable, I also did this here, or did I even get so far that I adjusted my runtable slightly? We can do this. No. If else string detect treatment. So now I have added here a column which says albuterol yes no, and a column which says dexamethasone yes no. And then I save this in my run table. Now I have a slightly better run table which also has these dexamethasone and albuterol things. If I now use this thing, I can now subset my DDS object, because DDS now has this factor albuterol, which has no and yes, and for now I only want to see the effect of dexamethasone to not have this complicated many by many comparison. So I say give me DDS only with these things. Now DDS dexa now contains only 7 samples. I run it like this, and it should now design treatment. It should now give me the result we have last time about the effect of dexamethasone. I should really just continue from that one, because the other one doesn't. This here has the. It already worked last time, so let's stick with this one here. Cell line dexamethasone. Final dispersion estimates. Fitting model and testing. So, in the end, I get my results. And if I now look at these results, you see here it gives me results. It explains again what results this is. That's important to look at. We look at the comparison dexamethasone yes versus no. And we now get all these things here. For example, here the log2 fold change. There's now different ways how we can visualize this. And one way to visualize it is this thing here. Let's make this a bit bigger. This is what we call an MA plot. each dot is one of the genes. On the x-axis the normalized counts, on the y-axis the fold change. And something that you immediately see is this characteristic trumpet shape. For weakly expressed genes, we get really strong fold changes, and for strongly expressed genes, we get quite weak fold changes. Also, we get quite a lot of fold changes here. Whereas, if you take the red ones, these are significant genes. If I quickly ask how many there are, at a forced discovery rate of 0.1, still have, these are 1,300 genes. What do you do with so many genes? Most people use these, and when they go into one of these gene set enrichment tools, where you look at all the genes and ask, are these genes enriched for certain gene sets? For example, are there more than usual, more than average amount of genes in the extracellular matrix, or genes which are part of a certain organelle, or genes which are part of a certain signaling transductions cascade, or whatever. And this might give you a hint of it. But another thing that one should look at is that you ask, what are actually the strongest effects? Clearly, these things here, the fold changes up to 4 on the log2 scale. Always remember with the log2 scale. So this is 4 times up, this is 16 times up. So these are probably much more important to understand the biological effect of dexamethasone than these small things which came only 10% up. Strictly speaking, if you think about it, we have a conceptual issue here. When people test for differential expression, what we always test for is, you remember, whenever we test and get a p-value, we have a null hypothesis. What we are doing here is something like a t-test, slightly more complicated. We'll explain later what exactly happens. And this null hypothesis is the gene is not differentially expressed. Its expression is exactly the same in the dexamethasone case than in the control case.
Now, which p-values did we use here? Is this the adjusted p-values, or?
The red color is the adjusted p-value, and I haven't yet explained to you the adjustment procedure. Where is my? Oh no, it's gone. Is it not still here?
And those 1,000 genes are the genes that are then adjusted with adjusted
yeah.
p-values adjusted 1.1.
Yes, let me quickly try to find something for you, and in order to understand this better, the first thing that we now should do is, let me undo what I did last time. Log scale X. Hope that this happens to work out of the box. No, give it a moment. Error object res. No, it's not res. Res. Who sees still where I put the word? Here. Anybody see where I still have in chart B1? Here. So, I'm jumping a bit today. A, I'm not that well prepared, and B, I want to show you a little hint of several things, and then go on a bit more. But didn't I just make a results object? I just say, it's res file, res dexa, titles 2, gene not found, and where's my gene? Here's my gene. I'm getting to it. Okay, this won't work today. So, let me try to explain it while this thing runs through. In principle, the way how you can look at it is, imagine we add dexamethasone, which engages some receptors, and then this engages some transcription factors, which will change some, cause some which will cause some genes to go up and other genes to go down, and these of course will again contain transcription factors which again affect something. In a way, if a cell senses that the conditions have changed, all genes will somehow react. Some genes will react directly because they are downstream of the affected transcription factors. Others will just happen to be affected by some crosstalk between two downstream signaling, which are affected by another transcription factor, which comes from the third transcription factor. But our traditional null hypothesis is that there is exactly no change. In the case of what we had at the very beginning of a lady tasting tea, our null hypothesis is that it's pure guesswork, that she has no way to say whatsoever. In classic statistical questioning, we have questions like, is there any connection between your astrological zodiac sign and your fate? And our null hypothesis is exactly 0. In biology, at least for a cell where everything is interconnected, this doesn't make sense. So if you ask me how many genes are differentially expressed, and I ask you, what do you mean by differentially expressed? And you might say, well, that its expression changes under treatment. When I can give you an exact answer, which is always true, and it's all genes. Every single gene is always differentially expressed if you do something. What you really want to know is which genes are strongly differentially expressed, and what you also might want to know is, do they go up or down? So is the sign that you read off in your RNA-seq experiment actually the right one, or is it the wrong one? And to show this, I have done this thing here, which to the left is this MA plot that you've already seen, and to the right is now the individual data. So each of these 4 rows here is each of these 4 columns is one of the 4 cell lines, and the blue one is untreated and the orange one is treated. But and now we can see here what these things is. You see here there's, for example, one gene which is arachidonate 15 lipoxygenase type B, and that one is one of those with the strongest effect whatsoever. In an untreated case, it's down here at blue. It's down at 0, but in the treated case, it goes up to maybe around a few hundred reads. This gene also has a quite good p-value probably. If you look at it here, it says p-value 10 to the minus 6. And probably this is consistent. It always goes up or down a bit. This, you see in all 4 samples, the orange thing, which is treated, is consistently above the blue thing. But that's probably hardly an as biologically interesting gene as that one. Now, one issue here is, if you now want to go down and follow a few genes which are actually interesting, you might look at those genes with the highest fold change. So what most people do is they sort the genes by p-value. There's not much point of it, because whether a p-value is 10 to the minus 20 or 10 to the minus 50 really doesn't make a difference. Once you have something like this, where all 4 samples react as strongly in the same direction, we believe it. What we're more interested is what is actually the standard error of this change. Here, for example, the fact that it's significant means that at least we can be sort of sure that the sign is correct. While if I go there in the orange area, you might now see in some cases the orange thing is on top, in others it's on the bottom. So this gene reacts, but the reaction has so much noise overlaid that we can't really determine whether it reacts upside or downside. It reacts because I say all genes react. So what usually a p-value in a differential expression experiment actually means is it answers the question, have we gotten the sign right? Is there a good reason to believe that the direction of change is the correct thing? It doesn't tell you anything about whether you got the magnitude right, only about the direction. Hence, there's 2 things which we now have. One is maybe we shouldn't care about this at all. Once the magnitude is large enough, we probably do get these things right. And for this, DE-seq now has this new thing which we call the log fold change shrinkage. Because here, these things were probably not true. You see that even the non-differentially expressed genes, so those where we are not sure about the sign, have changes up to 10-fold up or down, simply because we are here in the realm of, in the region of having only 1 or 2 reads per sample, and whereas a read extra might let the fold change appear 2, 3, 4 times. So what we actually want, we want to shrink down these exaggerated fold changes such to have them both on the same time. So for today I will just show you how it looks like by using this new LFC shrink thing, and about the actual details of the R code we do next time probably, because somehow everything got a bit too slow. And let's see if I still have here, let's put in here now the shrunken values, and at the bottom here as well the shrunken values, and let's see how this now looks like. Takes a second to get all the data from there to the browser. Now you see the MA plot looks very different. All those things which are not significant have been shrunken down here to 0, and now we see quite clear what stuff has strong effect, something like this gene here or that gene. And our long list of thousands of differentially expressed genes, we can probably downset and say here is some region of maybe 50 genes which are really much stronger than the other, and here are some 50 genes which are probably much stronger. Here's even one at the very bottom. That's again this lipoxygenase, it's still up here. Here now we have other things which, even though they are so far small, seem to react strongly. Actually, I now remember when I tested this last time, I noticed I have a sign wrong. So these are the genes which are upregulated under dexamethasone. These are ones which are downregulated. So this is another way of looking at your RNA-seq data, that you just look at those couple of 10, 20 genes which react really strongly instead of pushing them all together. Now, as I said, things are a bit busy. I've pulled a lot of different things together. So what I've shown here today is, first, we recapped our analysis thing. Second, we looked a bit at individual genes to get a feeling of how these things typically look like. And, oh, this is a nice one. Here, for example, you see something where 2 of the cells react strongly to this and 2 don't react, which is something which is considered non-significant, but it shows you the value of trying it on many different cell lines. And in order to demonstrate this to you, I showed you here this useful little web app which allows to inspect the data. And that's something which we are currently trying to promote in our group. This is now actually a glimpse in sort of our group's current work. We feel that it's really a problem that people always do this complex analysis and get this one little result table, and then you go on from that. And when you have a result and you wonder, is this typical or not? And in order to know what's typical, you have to be able to just inspect many of them and just get a feel of what happens at different places in the data. And often what you then have to get an overview of what can happen, you get a summary plot like this MA plot here, which you just plot using some ggplot command in R. And then you have then if you now want to see what's behind that one or that one, you always have to write dozens of R lines to get there. You first have to find out which gene is this, then you have to copy the gene ID, you have to type it again. Or maybe you have some specialized tool, some RNA-seq explorer thingy that somebody has written his master thesis on, which allows you to look into this thing in such a way, like here, specifically for one data set. And what we are now working on is to give you the tools to be able, within R, to just quickly put together something like this. So here is the total code that I've now always used to do this. And I quickly show you this here. If I manage to make my... It starts here with RLC for R-linked charts, because we are linking these charts, that's how we call it. We, by the way, means Svetlana Ovchinikova, a PhD student in my group, and me. When I open a page with a 2x2 layout, 2 rows, 2 columns, And now I simply here describe the first plot, the top left plot. It's a scatter plot. And on the x-axis is the base mean, on the y-axis is the fold change. The color value should be whether the adjusted thing is below 0.1. The size of the points is 1. There's a log tail. So this looks no more complicated than a ggplot command, even though it has a slightly different syntax. The same for the next scatter plot for this one here. Also, x-axis is which cell line it is. You see here the cell lines 1, 2, 3, 4. Y-axis is the expression of this gene. So we just take the count matrix and look up here at the place gene, and the color value is again whether it's dexamethasone treated or not. And the last one, this here simply says, take our result table and show me the gene which is there. And the only way how we get this clicking is this here, that there is here an on-click value which says whenever the user clicks on a point, please execute this code here and tell this code where the user clicked. The user clicks on K, so R puts into K where it is. This is then written in this function gene, in this variable gene, and you see the variable gene is used here to tell this plot what to plot, which line to plot, and once you tell it also update the charts or redraw the charts A2, so this one here, and B1, you get this. And you can imagine that any kind of complex data you can quickly bring in this shape by quickly doing the static plots you want to do anyway and connecting them in this manner. So this was now a bit a hot process. I apologize for that. Of different things that I wanted to show, I still haven't managed to find the time to explain what p-value adjustment means. So we'll get to that maybe next time. You've seen a bit how you can inspect RNA-seq data. We should talk a bit more about how to do complex designs, like, for example, they had this double drug, how good experimental design should be made, how many replicates we need, why they seemingly didn't have replicates. Each cell line drug combination was only once, and why this is still fine. All this not next Wednesday, because I'm in Munich next Wednesday, but probably the Wednesday after that. And I'll try to write up the commands from the from all the alignment stuff and put it online so that you can look through all this complicated workflow that we did last time and try to recap this time. Okay, thanks.
I have one question to this LFC shrink that you showed.
Yeah.
I mean, is that also applied for proteomics data? Because it would sound like a lot of
yes.
sense, right?
So this shrinkage problem is especially acute in RNA-seq, because in RNA-seq we often interfere with only 3 or 4 reads. This is because in RNA-seq we count discrete stuff, like these like reads. In proteomics we usually use MS1 intensity. There used to be a time when people looked at spectral counts, but luckily we stopped that. And MS1 intensity is continuous, so we don't really have that much this problem. We rather have the opposite problem, that weakly expressed proteins will have a too much shrunken rate, which might need to be blown up. The other issue is that you have zeros which are always treated improperly, which is actually also something we are working on in my group, but I won't get into this here. The other point is this whole shrinking of drop fold changes is reasonably new. So with LF shrink that I've just appeared here, we tried this in the original DE-seq because this was something we always thought that this needs to be done. Not only us, even in microarray times people already talked about the need to do that. In DE-seq 2, the shrinkage option that we had never really worked that well. Mike Love, who was the first author back then and worked as a PhD student with me and now has his own group, he actually revisited this problem, finally had a brilliant idea how to get the whole thing to work, got a PhD student to work on that, and their paper which describes the shrinkage that I've just described to you is a paper which appeared only last month. This is also why I'm not that familiar yet with how it works, but we can later, for example, compare how it works without and with shrinkage and how the ranking of your genes now completely changes due to that shrinkage. Okay, other questions? Then let's see you all in 2 weeks.